Thanks very much for coming to this talk. I think the topic of quantum communication and quantum internet is the most exciting field there is in science, and all of science and all of engineering. To build a quantum computer or to build something which could be called a quantum internet is incredibly difficult, both for the scientists and for the engineers. So with my talk, I hope to convey a bit of the excitement that I have for this field and that exists in this field. I also would like to give you some intuition for what the thinking is like in the world of quantum physics. When you read, or when I read or listen to talks, like TED Talks, 15, 20-minute TED Talks or so on this topic, I never really understand what they're talking about. So you do need quite a bit of time to get into this field. Maybe if I could just have a show of hands, who took a one-semester quantum physics class? Okay, so like 10, yeah. Okay, so maybe not too many, yeah. So there is a lot of excitement today in this field. I mean, quantum physics is a pretty old theory. It's almost 100 years old, and a lot of what was, or pretty much everything which was figured out about 100 years ago, still stands. So why all of this excitement today? And so that's what I'm going to also explain to you. Is the subject difficult? I think it is. It's difficult. Sometimes the math is difficult, but not always. It's difficult because the way quantum physics works, quantum physics, that's the physics of small particles, of atoms, of electrons, of photons, is just very counterintuitive. It's just weird. It's not something which fits with the intuition that we as human beings have of the world. So that's what makes it very difficult. Okay, so I will go through, I will go take you on a journey, and this is the way how I plan to do that. So I will give you a tutorial on quantum physics, and then I will go into detail in how teleportation works, quantum teleportation, then how quantum key distribution works, and then I'm going to explain to you how a quantum computer works. I try to leave out as much as possible mathematics, and I don't really assume that you have a physics background, but nevertheless, the going will be tough at times, probably. You may be baffled for two reasons. You may be baffled because my explanations are not good, okay? Or you may be baffled because everyone else is baffled, including the scientists that work in this field are just baffled that this is the way things work. So I hope you're baffled because of the latter, mostly. Okay, so we start immediately with a definition of a qubit. So first, a classical bit, and that's described as a unit of information. So that's any system that can exist in two states. That can be a coin, head or tail. That can be anything that is up or down, or left or right, or 0 or 1. So any system with two states, that's a bit. And the entire computer industry is based on the concept of a bit. So this is a mathematical abstraction, but that's an easy one to understand. There is a physical realization of a bit. It could be that the voltage is 5 for one state and it's 0 for the other one, or that there is a current flowing, no current flowing, or there is something is magnetized or not magnetized. This is how a bit is realized in reality. Now, a qubit is a two-state system where the two states exist in a superposition. So superposition is a fancy word for saying a combination, a sum of the two states. So that's the most important concept of quantum physics. You just have to accept it. That's the way it is, and no one understands why that's the way it is. The physicists use an unusual notation. We don't have to, with this bar and this bracket here, so we don't have to worry about that. So this is just how we label quantum states in this talk. So this is just amazing. Yeah? So if your son or your daughter or your spouse or your friend asks you what is a qubit, one thing you could do is to explain what a bit is, yeah, and then you say, you take out you take out a coin, yeah. So a bit is two states, so that's one state, and that's the other state. And the qubit, then you take your coin, and you spin it. And you could say that's a superposition of the states. So is that a good picture? I don't know. If it helps you remember what a superposition is, yes, but we don't really know how things work on this small scale. We don't really understand the private world of electrons or photons or protons. So sometimes people say the two states exist at the same time. Now, others say, we don't really understand what that means. What does it mean that two states, that the system exists in two states at the same time? That's maybe it helps some people to think like that. That's a figure of speech. I think the safest thing to say is you have a system of two states, and they can be a combination, that can be a superposition, that can be a sum. And these alphas and betas are called amplitudes. It's just a name for now, but we'll see what that is. So the next thing, which is amazing, is that these alpha and beta are complex numbers. So complex number, that's a mathematical term. Square root of -1. I'm not sure whether anyone has heard of square root of -1. These are imaginary part of a complex number, but we don't have to worry about that. For us, it suffices to say that these alpha and betas can be positive or negative. So that's, again, amazing. Yeah, you describe a state, and you have alphas and betas that can be negative, and I'll get to this in a few seconds. What that could mean. So with respect to the nomenclature, so on the top that's the physics nomenclature. You can also write a qubit in this what's called the vector form here, and if you want to do some mathematics on this. The field that's useful to know is called linear algebra. So everything related to vectors and matrices, that's the background of quantum physics. That's another way of showing a state. So you have a coordinate system with two axes, and the two axes label the two states. And then any arrow, any vector here is then a linear combination of those two what's also called basis states. So that's one way to visualize it. Now, in the real world, so far this is a mathematical concept, a qubit, but this also exists in the real world. One way of realizing it is if you look at an atom can exist in different energy states. So the lowest energy state is called a ground state. You can shine laser on an atom, that it goes into an excited state. So you could treat the ground state and the excited state as a two-state systems. So that would be one realization of a qubit. This one is very, very common. There is something called polarization in the context of light. Light is sometimes described as a wave, sometimes as a particle. The word for the particle is photon. So photons or light have a so-called polarization. That's the direction of an electric field that's associated with the photon. So the way the direction in which this electric field is wiggling, that's called polarization. So if your electric field is wiggling up and down, that's called vertical polarization. If it's wiggling left, right, it's called horizontal. And photons coming from the sun are polarized all over the place. You can put them through a polarization filter, and then they come out either vertically polarized or whatever angle you would like to have them polarized. So you have here, again, two states. You can consider horizontal polarization one state, vertical polarization the other state. So that's very, very, very common. Another one is the spin. Spin is a purely quantum mechanical concept. The way it's often introduced is think of an electron that can spin around left, counterclockwise or clockwise. Not quite right, but it's that's one way of thinking of it. And spin can also, the usual nomenclature is a spin can be up or down. So you have two states, and this is also a very common system to use the electron spin as a two-state system. So you basically, you disassociate the spin or the polarization from the actual particle that the spin or the polarization is associated with. Then you can also have, there is something called superconducting electronic circuits. If you transport current through a wire, the wire gets warm. That's just because there is resistance. There's a concept called superconductivity, which means there is no resistance. And there is something called superconducting circuits. And you have to really cool down things to very, very low temperature. This is the IBM quantum computer. It's basically a refrigerator. You have to cool down to like 15 millikelvin. That's why it looks like this. Okay, superposition. Yeah, I think we have a feeling for that. The next thing, which is very important and really bizarre, is the process of measurement in quantum physics. So here is our what's called a state or qubit, which is a bunch of 0 and a bunch of 1, and we call the alphas and beta amplitudes. So the amazing thing is that if you take these, well, strictly speaking, it's called the absolute magnitude squared, but let's forget about the absolute magnitude. Let's just say it's squared. If we square these alpha and if you square this beta, we get the probability of finding the system in the state 0 or in the state 1. So it's just amazing. Yeah, that's just the way it is. No one really knows why that is, but that's the way it is. Thousands of people over the last 100 years have done theory and experiments on quantum physics, and that's just the way it is. Yeah, we square these amplitudes, and then we get the probability of finding the system in a state. And so the probabilities add up to 100% or to 1. So the saying is you have to normalize alpha squared and beta squared to 1. Okay, next thing is, amazing thing is you cannot measure alpha and beta. So that's totally weird. When you do a measurement, you always get either this one state or the other state with a certain probability. It's random. You don't know beforehand which state you'll get, but that's what you get. So that's totally bizarre. The next thing is you cannot predict. You don't know when you take a measurement, will you get this state or will you get the other state? Totally bizarre. Amazing. I put here in general, the only exception is, suppose you start out with the state on the top, you do a measurement, and suppose you receive the state 0. If you take then this same state and you measure again, you get again with 100% probability your state 0. But in general, you just have no idea. You don't know what you're getting. So what you would have to do, basically, in order to figure out the alphas and beta, I would have to give you an infinite number of systems prepared identically. And you do measurements on an infinite number of systems, and then your statistics will be good enough to tell you what the alpha and beta are. Totally weird. So if I do a measurement, I'm actually altering the state of the system. Again, bizarre. Yeah. So this measurement process is difficult to understand, difficult to get used to, but that's the way things seem to work out. Is that the right slide here? I guess, yeah. I'll start with this first. Another concept which is important is to understand interference. So a lot of the mathematics is in terms of waves in quantum physics. So interference just means you can add up, or you can add up waves. And on the right-hand side, if they are in what's called in phase, you add up the waves and you get a constructive interference. And if they happen to be shifted, yeah, it's called shifted in phase, you may get destructive interference and you get nothing. So the quantum world, obeys different laws of probability than the ones you're used to. And the ones we're used to is that the weather forecast says that the 30% probability that it's going to rain. So in the quantum world, you could say there is a minus 70% probability that it's going to rain, so to speak, or a minus square root of 55 probability. So this is just weird stuff. And the secret of quantum computing, and I'm going to repeat this a bit, is you have to choreograph your algorithm in such a way that these amplitudes, these probability amplitudes, the right ones amplify, and the wrong ones, that they cancel each other. That's the secret of doing quantum computing, but we'll get to that. There is, this superposition of states is so baffling. And Einstein, Schrödinger, two of the main people that helped build quantum physics, they just kept thinking of this. And so Schrödinger and Einstein, they came up with what's today called Schrödinger's cat. Suppose you put a cat alive in a box, and you have a source of radioactive atoms in there. So radioactivity, atoms decay, but the process is totally random. You cannot predict when one particular atom is going to decay. So a atom decays, and then it triggers a mechanism. A hammer is released, falls on a flask. The flask, this bottle of glass, has poisonous gas and kills the cat. So how would you describe the state of the cat? You would have to, you don't look inside the box, you're looking outside the box. You don't know whether radioactive decay has already happened. You don't know whether the cat is dead or alive. You would have to describe the state of the cat as alive, a bit of alive and a bit of dead. It is weird stuff, yeah? And there are different interpretations of quantum physics that try to make sense out of it. All the interpretations are not quite 100% conclusive, so that's still an active field of research. So here is what physicists, I think you will maybe understand the humor here now. So it says, how's your quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful and not even started. So that's the superposition of state, yeah. And then, can I observe it? That's the measurement process, yeah. Well, that's a tricky question, yeah. So let's say Dilbert cartoon. Okay, an example here. So I'm asking you, here is a state, square root is supposed to be 1 over square root of 2, and then state 0, state 1. Again, think of this state 0 and 1 of a polarization of a photon in this direction or in the horizontal direction, yeah? Okay, so here is what is this state vector normalized? So normalized means that the alpha squared, the beta squared need to give 1. So what's the answer here? It is normalized because if you square the first term, that's a half, the second term a half, adds up to 1. Okay, good. Now what's the probability of finding the system in state 0 after measurement? So the probability is given by, we look at the amplitude, so the number in front of the 0 state, so that's 1 over square root of 2. So what's the probability of finding it in the state 0? We need to square the number, which is 1/2, yeah? Now, suppose you have measured, you have done the measurement, it's in the state, suppose it turns out to be in the state 0. You do again a measurement. In which state will you find it? You will find it again in the state 0. Yeah, that's the only time where you know 100% sure that your measurement is not just a probability. Another one here, 1/2 minus square root of 3 over 2. So is it normalized? Yes, it is normalized because 1/2 squared is a quarter. The second term squared, that's 3/4. So together is 1. Again, what's the probability of finding the system in state 0? What? 1/4. Okay, 1/4. Yeah. So that's the first term squared. What if I were to measure the system in state 1? What would be the probability for finding it in the other state? 3/4. Yeah. So that's a sort of the thing that this is the bread and butter of quantum physics. Okay, what about this here? What's the probability? Well, maybe first, is it normalized? Yes, it is normalized because the number in front of the 0 state is a 1. 1 squared is 1, so it's normalized. So what's the probability of, if you do a measurement, which state do you find it in? You find it in state 0. Yeah. So the number in front, so the number in front of the 1 state is 0, 0. But there is just the 0 state left. So and alpha is 1. Okay. an important theorem in quantum physics is the so-called no cloning theorem. In classical physics or in computer science, you can copy bits. Yeah, we do this all the time. Yeah, you can, in memory, you copy stuff all the time. In quantum physics, you cannot copy qubits. Yeah, so that's good and bad. It's good for security if you do develop security protocols. It's bad if you would like to copy stuff the way you do copy stuff in computer science. So, but that's the way it is. Now, this sheep here is Dolly the sheep. I'm not sure whether you're old enough. About over 20 years ago, sheep was cloned. You know, people keep cloning animals. Why can you not clone qubits, but you can clone sheep or animals? I wasn't quite sure what the correct answer is. Yeah, I read an answer, but I didn't quite understand it. So I'll just leave this here as a puzzle. All right, now we are combining qubits. So far I was talking about one single qubit. Again, one single qubit in a system that can exist in two states. Now we are putting more than one qubit together. We're going to 2 qubits, 3 qubits, and so on. So putting 2 qubits together. Classical physics, you have then 4 possibilities. Yeah, here they're written down. So in quantum physics, you have, again, these 4 basic states, and they can exist in a superposition. Yeah? This is how it's written, and you have this normalization condition that the probabilities need to add up to 1. Now we go, so this is another way of writing it. You know, so that's just nomenclature. If we go to 3 qubits, yeah, in classical physics, you have 8 different possibilities of arranging 3 qubits. So what you do in quantum physics for a 3 qubit state, you add up all these 8 combinations. That's the way it's written, and you have to see again that this is normalized. So now you can continue this. You go to many qubits, and this is what you'll get. Next topic, entanglement. That's probably the weirdest concept that there is in quantum physics. Entanglement is something you have to have at least 2 qubits. You need a system of 2 qubits or more. Yeah, not with 1 qubit. You get entanglement with 2 qubits. So the word to entangle means there is a certain correlation. There is a connection between these 2 qubits. You cannot describe, if you have entanglement, you cannot describe 1 qubit without taking the other qubit into account. There is nothing romantic in the relation in entanglement, yeah, but maybe this helps you remember the concept a bit. You can separate the 2 qubits and the entanglement still persists. You could go to the next star, which is Alpha Centauri, which is 4 light years away. Light means 4 years to travel there. If you start out with entangled qubits here and you move 1 very far away, there is still this connection, this strange correlation between the qubits. Entanglement is not an all or nothing feature. You can have partial entanglement, you can have different degrees of entanglement, and you can also have something called maximal entanglement. Now, the true weirdness of entanglement is this here. You can know everything that there is to know about the composite system, but you know nothing about the individual systems, about your 2 individual qubits. That's really weird, that's strange, and people have tried to figure out for 80 years what that really means. So to give you 2 metaphors, suppose you have a car, and when we have a car, you know, we can dismantle the car, we can dismantle it in all its pieces, all the pieces of the car. If we know the car, it implies that we also know the individual parts of the car. Not if you have entangled photons, not if you have entangled qubits. Another picture, suppose you are reading a book. We have a classic book and we have a quantum book. Now in a classical book, you start with, suppose the book has 100 pages. You start with page number 1. You have 1% of the content. You read page number 2, then you have 2% of the context. You read page number 100, you know the entire content of the book. If you have a quantum book and you look at the individual pages, you see nothing, just gibberish. So all the information is contained in the relation that these two qubits have. It's a totally bizarre concept, entanglement. It's not just that you are baffled, everyone is baffled. So on top, again, we're talking about 2 qubits, and this is a general state that I've written on top. So some states are, depending on how you choose alphas up there, depending on that, you can have non-entangled states, and you can have maximally entangled states, and these are very famous states. If you work in this field, you will know them by heart. These are called belt states. There was a physicist that was also working here at CERN in the 60s, 70s, and EPR, the E is for Einstein, so they're called either belt states or EPR states. So we're going to use them later when we talk about the balloons here. So if you have unentangled states, again, we're talking 2 qubits, yeah? If the 2 qubits are not entangled, if they're unentangled, if I do measurements on 1 qubit, then I have no information, I don't know anything about the other qubit. But if I have maximally entangled qubits, if I measure my qubit, if I do a measurement on a qubit that I have, it doesn't tell me anything about my qubit, but I know if I do a measurement, I know immediately what kind of measurement the other person would get if he or she were to do a measurement on their qubit. It's totally bizarre. So for example, suppose I have like in one of these previous belt states that I showed you, 1 qubit is, let's call it spin up and spin down, well, let's take maybe let's take the top state. If I do a measurement and I find my electron in spin up, then I know immediately that the other spin will also be up. Or I could have a system where if I measure 1 spin up, I would know immediately that the person, were he or she to measure, do a measurement on their qubit, would get -1. So, but when I do a measurement on my qubit, I have no idea whether I would get up or down, 0 or 1. It's completely random. It's 50% chance. But once I've done a measurement, I know immediately what the other person would get if he or she were to do a measurement. Again, it's a totally bizarre concept. Einstein, this is a term that you will often find in the press, spooky action at a distance. I have 2 entangled photons. I separate the photons. I move one qubit or photon to the sun, and I'll do a measurement here, but this will influence my qubit at the other end of the universe. Yeah, totally strange. Okay, now I'm going to describe like the experiment that captures all of the mystery of quantum physics. It's called the double slit experiment. So Newton thought light was a particle. Then there was a person called Young in the 1800s, around 1800. He showed beautifully that with the double slit experiment that light is a wave. And then Einstein, 100 years ago, then showed again that some experiments need to be explained with thinking of light as a particle. It's also shown that electrons, particles, behave like waves. So what is it? What is light? Is it a particle? Is it a wave? An electron? Is it a particle? Is it a wave? Who knows? So here, I'll show you 4 scenarios. Here is a setup. You have a gun, so maybe a machine gun, and it can spit out bullets. You have a wall with 2 slits in it, and you just fit about, you're just big enough so that a bullet fits through. You have a detector that can go up and down, or you can have a lot of number of detectors at what's called the backstop. And now you measure where the bullets hit the backstop. So if you close one hole, then you get the distribution which is labeled P1, yeah, which makes sense. Yeah, there is a certain distribution. The bullet may hit the edge here that gets a bit deflected, but sort of this distribution that you see makes sense to us. If we close the other hole, yeah, we close hole 1, hole 2 is open, we get the probability distribution which is described by P2. And if we have both holes open, then we get the probability distribution that's called P1, P2. So the bullets, they come in lumps and there is no interference. So we understand that. Now let's do the same thing with water waves. Again, you know, same thing, you have a water source, you somehow have something which goes up and down and it generates waves. Let's assume that we close off one hole. Let's say hole 1 is open. Then we get and if we measure let's call it intensity, which is the height of the wave squared, but that's a detail, let's not worry about that. We get this intensity distribution, which is labeled I1. If we close hole 1, we leave hole 2 open, we get what's described by I2. But now, if we open both holes, we get this interesting looking distribution, which comes to about, and which we understand is because water waves, they interfere. Yeah, if you have the water waves which are in phase, then you get the height of the water wave is big, and if they are out of phase, then you have destructive what's called interference. Okay, so that's what we understand. Now that's the weird thing. Now do the experiment with electrons. You close off one hole, and it's like with our bullets. This is where the detector is going to detect the electrons, described by P1. You close 1, and you open 2, and you get what's described by this probability distribution P2. And when you actually measure the electrons, and whenever the electron hits the detector, it does click. It comes in lumps. Click, click, click. Now you open both, and you get an interference pattern. This is totally strange. Yeah? So you have the electrons coming in lumps, but you have interference. And if you to decrease the number of, if you shoot one electron at a time, you do get this interference pattern. So you're wondering, man, if I shoot one electron, and do they, if you shoot maybe many very fast, maybe you could think that the electrons going through 1 and through hole 2, they may interfere, and that's what causes the pattern. If you do the experiment with just one electron, one at a time, click, click, you still get an interference pattern. Totally weird, totally weird. Do they go through the same slit and they interfere somehow? Totally strange behavior, but that's what it is. This is actually an actual an experiment that was done with electrons. You see the interference pattern. Now the thing which is also totally weird is, well, you want to maybe can you figure out which hole an electron is actually going through? So you put a light source right behind the slits, and when an electron hits light is being scattered. That means it's being deflected. So if an electron goes through hole number 1, we should see a little flash in this vicinity. If the electron goes through hole 2, we should see a little flash there. If you do that, if you look where the electron goes through, the interference pattern is gone. Totally baffling. Yeah. So everyone is baffled by that. It's not just that we are baffled. All the physicists that have worked on this, they're just baffled. That's the way it is. Okay, so there are about 10 so-called interpretations of quantum physics to make sense of that. One is called Copenhagen interpretation. The reason why it's called Copenhagen, because Niels Bohr, who is a famous person, physicist, had his institute there. And that's sort of the de facto interpretation. And it says that, you have your system in this superposition of states. When you do a measurement, then your system collapses into one of those states. So what does this mean, to collapse? What does it mean to make a measurement, to observe? If I'm observing an electron, then the interference pattern is gone. What about if a dog is observing that? Does this have? And these are all things that are being discussed here. So That's one. And if you think this one is crazy, this one is even crazier, called the many worlds interpretation. Now, I'm not making this up here. People think that, for example, in the case of the Schrödinger cat, or no matter which system you have, where there is a possibility for a system to go either this way or that way, that the universe is splitting into parallel universes. I mean, I don't get it, yeah. But they're famous, famous physicists that think that. And one person who did a lot with respect to quantum computing, he is a total believer in this many world interpretation. He doesn't understand that no one else believes it. I mean, there are some quite a number of people think this is what's happening, but I'm just totally, that's beyond me. So the history of physics, what still stands, was figured out about 100 years ago. Is there anyone among you who knows the names of, say, more than 3 people? Well, I think we all know, Anj. You know more than 3 people. Okay, that's pretty good. Okay. Anyone knowing more than 6 people? Oh, that's still pretty good. Okay, that's impressive. Okay, good. All right, so the excitement today is often called a second quantum revolution, and it started in the 80s. There were basically 2 independent, sort of streams. One was with respect to quantum computing. Richard Feynman said, the whole world is based on quantum physics, so a computer should also be based on quantum physics, not on classical physics. So he said to really study atomic systems, your computer should be a quantum computer. And then also on the communication or information side, the development of what's called quantum key distribution protocols. So we'll get to that. All right, now to the teleportation. To explain what teleportation, quantum teleportation is, I will first start to explain what it is not. Here is a heading from BBC, which says teleportation photon particles today, humans tomorrow. And then Chinese, below it says Chinese scientists that they have teleported a photon particle from the ground to a satellite orbiting 1,400 kilometers away. So very often what you read in the popular press is at best misleading, and often it is wrong. So we'll come back to this at the end of this quantum teleportation piece, and then we'll see again whether this is correct or not. I'll give you maybe a one or 2 sentence explanation what quantum teleportation is. You may not understand it immediately, but we'll go back to this at the end. So when you have quantum teleportation, you are transporting information. You're not transporting matter, you're transporting a qubit without actually sending the particle that the qubit is associated with. Think again of a photon. Photon has polarization. So you can transport the polarization, the state of the polarization, without actually transporting the photon. But we'll get to that. You'll understand that better. Here's another cartoon here. So there's a journalist that says, okay, so quantum teleportation. And the scientists say, the name is misleading. It's a star particle statistics thing. So and the journalist says, oh, so it's not like Star Trek. Oh, that's boring. Okay, and then physicists, I'm sick of this. Every time there is a paper on quantum teleportation, your reporters write the same disappointing story. Yeah, they think of Star Trek and science fiction. Yeah, and then the scientist leaves, talk to someone else, and he's really pissed. I'm going to the Bahamas, and the way he's going to the Bahamas, he's actually going into a teleportation machine. That's just the thing that he hates the journalists talking about, because that's just not what it is. Yeah. Okay, so when I grew up with Star Trek and Captain Kirk and Spock, yeah. So in science fiction, teleportation is that an object disappears magically here and shows up magically somewhere else. Yeah. So Kirk and Spock and so these people, they get beamed, they get beamed down or beamed up. They disappear here and they show up magically somewhere else. And this happens instantaneously. So that's the science fiction version of teleportation. Now, is sending an email or a fax teleportation? I mean, it's certainly magical. Yeah. I'm sending an email, it shows up in Australia a couple of seconds later. Wow, that is magic. But it's not teleportation in the sense of quantum teleportation. Because when I'm sending an email, the waves are sent to the access point here, then it goes to a fiber cable. Does it go to a fiber cable afterwards? Yeah. Fiber cable, then it goes across the ocean in fiber, and at the end in Australia also goes to a Wi-Fi access point, and with electromagnetic waves to a smartphone. So there is information, there's stuff being transported all the way along. So that's not teleportation in our sense. What about 3D printing? You know, I have a teddy bear. I could do a 3D, you know, I could scan it. I send the scan over the internet someplace else, and I print it somewhere else. That's not teleportation in the sense of quantum teleportation. Remember the no cloning theorem? Yeah, I would have 2 teddy bears here. In quantum physics, you can't have that. Okay, now let's try that. Holograms. We have a focus group called Network 2030. And if you listen to the talks, or if you see what's being discussed in there, is Huawei describes a service that they call hologram. I have to see, I have a slide with what they call it. They call it holoportation or so. And it's a fantastic name. It's a fantastic marketing name, but it's not teleportation in the sense of quantum teleportation. So here is actually a, can we play this now? Yeah. So this is a, the person is a scientist and also a musician. He's in Berlin. His daughter is in London. And what you see here in Berlin is a hologram of his daughter. Does it play, or is it going to work? Maybe not. Can I do this here? Okay, takes so much time. Well, maybe it does take time. So what he's playing is a slow piece of music. It's pretty. The reason why it's slow is because he needs to be synchronized with his daughter. The daughter needs to be synchronized with her father. It takes time for the signal to travel. So the piece is slow, and we can play that. So, I mean, a hologram is, there's some way of generating holograms. What you can do today is you send the information and you generate the hologram on the receiver side. That's what's being done. So that's what's being done there. And but you need a lot of computing power to do that. So what Huawei is envisaging for the 2030 network is that you build the hologram on the sender side and then you ship it across the network. But for that you need huge bandwidth. So that's what our network 2030 focus group is trying to do. So again, you know, but there is information. There is not something disappearing here and magically appearing somewhere else. There is stuff happening in between. So that's not teleportation in our sense. So the teleportation protocol was discovered or invented about 25 years ago. And so these are the authors listed here. And I give you several different levels of description. Each level will be a little bit more complicated. So at the 100,000 foot level, we can go back to a Greek philosopher Aristotle, who said that each object has a substance and it can have a form. And in physics parlance, you would say that particles have matter or energy, and they can have a state. They can have a polarization. They can have a spin. So what's being transported is not matter, not energy. Transporting matter, transporting energy, or teleporting matter, teleporting energy, that's a science fiction concept, not possible. But you can teleport the state, you can teleport the form. So coming back to our teddy bear, what that would mean is that, you know, this stuff here on the bottom, that's supposed to be the material that you make teddy bears of. So if you teleport the state, what you have before teleportation is that you would teleport the form of the teddy bear to the sender side, receiver side without actually teleporting the stuff that the teddy bear is made of. I think this explanation might actually be more difficult to understand than the one that's going to come here. So let's go to the next level of detail. In order to do teleportation, quantum teleportation, you need to have already 2 entangled photons. Yeah, so there's a process, and somehow you can generate that, and then you give 1 entangled qubit photon, you give it to Bob, and 1 you give to Alice, and you separate them. And then Alice, we want to send a qubit from Alice to Bob. So Alice has a qubit that she would like to teleport. So what she does then is she has 2 photons. She has one of the entangled pair photons, and she has the own photon that she would like to teleport. And then she does some magic measurement. And as a result of that, she gets a result with a certain probability, and she communicates the result of this measurement to Bob. The way she communicates that is she picks up the phone or she sends an email. So that's classical communication. She communicates in 1 of 4 numbers. That's when she does the measurement, there are 4 possible outcomes of the measurement. And so one of those 4 outcomes, one of the 4 numbers she's going to send to Bob. And then Bob does some corrective operation, and then the state of his qubit of his photon is exactly the same as the one that Alice sent. So again, think of a photon. That's a particle. Particle is a bunch of energy. You can also think of it in electrons, then it's a bunch of matter. So you have a photon, and with the photon you have a polarization associated. And it's this polarization state that we are teleporting. We're not teleporting the photon, but the state of this photon. The state of this photon. So that can be teleported without actually sending the photon that the polarization is associated with to the receiver side. So we can demonstrate this. We'll do another round of that with balloons. So I have not Alice, but Ida, and I don't have Bob, but Bastian. So we have so this is our photon, and the polarization is supposed to be the form, the shape of this balloon here. That's the polarization, yeah. The stuff that the balloon is made of, the matter, and that's not, or the energy, that's not what's going to be teleported. So Ida, this is what Ida would like to send. She would like to send the polarization state, the form, to Bastian. So we need to start out with entangled photons. So this is, you have to prepare in advance. So I'll let this fly down here, yeah, and then, so I generate these entangled photons, and then the 2 separate. So Bastian can go to the sun, he can go to the end of the universe, it doesn't matter. Okay, so they're entangled, there is a special relation between the 2. So now, and this is what the mathematics gives, yeah, there is a little, that's just the way, yeah, that would take time to explain that. Ida does a magic measurement. And the result of this magic measurement is, these are our Bell states. These are the 4 Bell states that I showed you earlier. Yeah. So we connected the blue balloons, the orange, the red, the green balloons to indicate they're entangled. So I'll put this around your neck. So these are the entangled states. When Ida does a measurement, she will get, as a result, one of the entangled states. So this is a state to be teleported. Ida doesn't know the state, Bastian doesn't know the state. We took care of that. Yeah, we have a maximally entangled state. Yeah, we have this indicated here. And then I think, so Ida, she has 2 photons. Yeah, the one that she would like to teleport the state of, and Bastian has 1 photon. And now, Bastian, I think you need this pump here. You need a pump and another balloon. So when she does the measurement, a whole bunch of things are happening at the same time. When Ida does the measurement, this entanglement is cut off. Yeah. So that's no longer entangled, but at the same time, Ida receives, as a result, one of these 4 entangled combinations. So I just pick this here. Now let's say this is this here. So there are four possibilities, and they're being measured with equal probability. Now there is a 25% chance that she gets the right there, or the blue, or whatever balloons. So let's say the result is this. So you have 4 possible numbers, 0, 1, 0, 1, 2, 3. So what Ida now does is, and at the same time there is a new entanglement happening between the stuff that she would like to teleport and this one. And then what Ida does, she communicates or is picking up the phone or sending an email to Bastian and telling him outcome number 3. Bastian knows outcome number 3, which combination, which state that is. Bastian on his, and at the same time, this here, this disappears to no cloning theorem. And now, Bastian, you have to pump on your side. The other one. Okay, so it's going to make a bang, but that will help you remember, perhaps. Yeah. So then on Bastian's side, he will, keep pumping. He will have the state, the polarization state that was originally with Ida. Yeah, and okay, be careful. So in summary, again, what you would like to do, or what you do with quantum entanglement, is you're sending a qubit. Yeah, think of a qubit as the polarization of a photon. You're sending the like the angle of the polarization. You're sending this polarization state that's described with this number alpha 0 plus beta 1. You're sending this information to someone else at the end of the universe. You're not sending the photon that the polarization is associated with. And this, I think the word teleportation is justified, because this polarization state just shows up magically at the other end of the universe, even though you didn't transport the whole photon with its polarization state to Ida. That would have been another possibility. Yeah. But no, it's this spooky action at a distance. Somehow, miraculously, this polarization state gets teleported to the end of the universe. It's absolutely baffling. Yeah. Pardon me? Yes. Yeah. So when Ida does her measurement, yeah, then this entanglement that she had originally with Bastian gets broken, and a new entanglement between her balloon and the other photon is going to happen. So that's a new entangled pair that you have. So what is remarkable is that the photon now with Bastian is absolutely identical to the one that Ida had. Even though the photon itself was not transported, you could not distinguish the polarization. It is exactly the same. Even though Ida and Bastian do not know at all what the state is. This alpha, beta could be anything. They don't know that. So this is an absolutely baffling technology. Yeah. Pardon me? It's for the use is that you can transport qubits without sending the actual photon. Yeah, but in order to do that, you have to start out already with an entangled pair. Eventually, in a quantum internet or in a classical internet, you're sending bits around. In a quantum internet, you would like to send qubits around. You would like to, yeah. So quantum teleportation is one way of sending qubits. Yeah. So how far can you do that? I think in optical fiber, it's about 100 kilometers. And the Chinese, they did an experiment with a satellite. They went up to 1,400 kilometers that they send entangled photons. So they launched a quantum science satellite in 2016. They had a whole bunch of experiments, and they have all been widely reported recently. So here is what they did. There is a ground station. It's called Ngari, and the satellite. How do I pronounce that? Shoya Mikius. You don't. Yeah. Doesn't. Okay. Different. Yeah. Good. So the same thing that we did here. Yeah. We have a state that we want to teleport from the ground station to the satellite. Yeah. The state is written here. You produce at the ground station, you produce entangled photons, and you send one to the satellite. Then you do this magic measurement, and then, wow, the state, but not the photon, but the state of this photon is teleported somehow magically to the satellite. That's what they did, and they had a 1,400 kilometer distance that they covered. So that's amazing. So now coming back, well, to this here, how can you teleport quantum states of bigger things like a virus, perhaps? Yeah. Would you be willing to step into such a teleport machine? Not now, because a lot of photons are still getting lost. I mean, this is sort of proof of concept. We don't know whether we would be able to do this eventually. Maybe yes, maybe no. Here is a slide from the talk that our chair of the focus group gave when we had the first meeting of the focus group of the Network 2030 focus group. There is one mistake on the slide, and you should be able to discover it. So they say holographic teleport in the context of communications, classical teleport, disassemble the object into pieces, ship it, assemble. Okay, maybe you want to ship a rocket, you dismantle it, you ship it, you assemble it. Okay, fine. Next one, quantum teleport, transfer of matter or energy from one point to another without traversing the physical space between them. That's what he calls quantum entanglement. And then holographic teleport, scan the object, and its actions and instructions, metadata, data, all together called this holographic package. Okay, there's a holographic package. You transmit it using a new telecom network, and then you reproduce the object in the form of a hologram on the other side. So there's one mistake here. What's the mistake? Pardon me? Yeah, okay. So that point is wrong, yeah? So quantum teleport, you do not transport matter energy. This is science fiction. You don't do that, yeah? The word holographic teleport, I think it's a fabulous marketing name. Just suppose you have to advertise to your customer, I'm all going to offer you a teleporting service. Wow, you certainly will get interested. Now coming back to this article, teleportation, photon particles today, humans tomorrow. We don't even, well, forget about humans, yeah? But not even photons. We don't teleport photons. We send the state that's associated or that's carried by a photon like a polarization. So that's already wrong. And then below, Chinese scientists say they have teleported a photon particle from the ground to the satellite. Again, the same thing. You don't teleport the photon particle, but the state. Yes, sure, yeah. Yes. I mean, what you do is you send information. You send information from Aida to Bastian, but what you send is just 2 bits. Yeah, you have these 0, 1, 2, 3 possibility as an outcome. You send classical image, just 2 bits. That's what you send, and then Bastian on the other side is able to reconstruct on his photon the polarization state. So that's wow, amazing. Yeah, sending a qubit, but you don't actually, you're not sending. You're just sending a classical information. Yeah, that's wow, amazing. Okay, good. Right. Okay, so that was this topic. Okay, maybe as a takeaway, yeah. Okay, maybe keep this in. Maybe if you can remember that, yeah. You don't teleport energy, matter. That's purely science fiction. You can teleport quantum states. Pardon me. A serious question. A silly question, yeah. Maybe microphone. If you turn on the microphone.
We are transferring a photon from Aida to Bastian.
No. No.
We are not doing. We are transferring the spin.
No.
The spin. The
no.
state.
The what you're communicating. No. No.
The state of the photon will be replicated there in a new photon.
Okay. Good. Yeah.
But to do that, we have to transfer a photon at the beginning. The entangled one. You create two entangled ones, and one you have to transfer there physically.
At the very beginning. Yeah. You have to start out with. That's the precondition. That's right. You have to start out.
My silly question is, you have to do that for every photon.
Yes.
So, what's the difference if you transfer the photon as you want, as you had it there?
That's one
possibility. In
possibility.
Any case, you have to transfer first a photon, and then you say, let's make this magic, and then we appear. But the transfer happened before with the entangled one. So I don't see what we are gaining if we did transfer directly the photon that we wanted to have replicated instead of the entangled one and then to do the magic. Maybe there is one less step to obtain what we want.
That's
also
a silly question. That's also a possibility. Yeah, instead of going through all this hocus pocus, yeah, you could just send the actual photon to Bastian. That's also a possibility. Yeah, but if you don't want to do that, yeah, maybe you don't want to do that, yeah. But for example, the satellite experiment with well, that you. When you can, for example, if you transport photons on the ground so far, there is a limited distance that you can keep your photons in an entangled state. Yeah, you can go to about maybe 100 kilometers. If you will go to longer, then that wouldn't work anymore. Yeah, if you could reproduce entangled teleportation for any point on the planet, that might turn out to be useful, interesting. Yeah.
So if I understand correctly, the teleportation, the quantum teleportation, requires also the classical communication in the measurement, right? Is teleportation possible without that?
You need to communicate. You need to communicate something from Aida to Bastian. And the reason, well, one reason why you also have to do that, suppose you did not have to do that. That would mean that you would have, and suppose then somehow Aida does its magic measurement, and immediately Bastian's photon would adapt the polarization state of her photon. That would mean instantaneous communication. Yeah, and the fact, and in physics you cannot go faster than the speed of light. So the fact that you actually have to send some classical information, that you have to send something, is obligatory in order to not be faster with not to be faster than the speed of light.
Well, I could argue if the photons are entangled, if I change the state of my photon, it would also change the state in the other photon, and there's nothing physically transmitted because they are entangled. Right?
You mean the pair that we have at the very beginning?
Yes.
They are entangled. Yeah, there is if Aida were to do a measurement on her photon, if she wanted to measure the polarization state of her photon, she
changes the state and also this.
So what would happen is she would have a 50% probability. Yeah, she would to measure it in a vertically polarized state or in a horizontally polarized state. A 50% probability. So she doesn't know before she does that. She has no idea. Totally random. But the strange thing about entanglement, if suppose she did a measurement, you were talking about the two balloons at the very beginning. If she did a measurement, she would know immediately what Bastian would get if he did a measurement. In this sense, there, not sure whether. Okay. Yes.
Yeah, sorry, maybe I can give a better explanation. Why is it different than transferring the photon directly from one place to another, actually the entanglement? If we make that the same way, the teleportation of the information can be done on different pairs of entanglement. For example, with photons, it's very easy to make the 1,400 kilometers without loss, and they are entangled. But we can transfer this quantum state between a pair of electrons, for example.
You can also do that.
The physical transport of entangled electrons is much more difficult than the entangled pair of photon to carry over the information. So that way we can really use the photons to carry over the state information between a coupled electron pairs to the electrons. So at the end, one electron state will be transferred to another electron, much higher distance. The physical transportation of an entangled electrons would be not trivial, same way. I don't know whether I gave good enough explanation.
I mean, I'm not sure whether I understood entirely. I mean, you can do the same. Yeah. Yeah. I mean,
physically an electron.
No, if you can send the if that's no problem, sending a photon in its state to any place in the world. Okay. Yeah. Maybe that's fine, but maybe some kind of services may be developed that for which this might be useful. Yeah, I don't know yet. Yeah, maybe I don't know enough about the field. Yeah, but I think it's an interesting Lego block that could be used in whatever service people may come up with. Yeah. Okay, so the next now how do we do that now? We have a section on quantum key distribution. So that's something which I think everyone will understand, the concept. And so it's amazing the way it works, but I think everyone will understand it. And then we have a section on quantum computing, which is a little bit tougher, part of it. So I don't know whether we want to take a bio break or whether we hang on. Continue. Individual bio breaks. My boss says, okay. All right, so before I explain quantum key distribution, it's important, I think, just to get a quick overview of the history of cryptography. So there are two books. I read the one that's called The Code Book. Super interesting. Yeah, you don't have to know mathematics, but it's just great. Also very good description of quantum key distribution. Very exciting book. The other one is a bit older, and when I read the Amazon reviews, I read that like every secret, every CIA, NSA agent has a copy of this book on his desk. So with one sentence, in cryptography, nothing really happened for 2,000 years since the invention of the cipher, except over the last few decades, there went boom, boom, boom. So this is the Caesar shift. Yeah, Caesar, that's the Roman emperor for our maybe people who may not know. And so it's very simple. Yeah, you shift each letter by like 3 or 4 or whatever number of letters. The Arabs, I think that was around the 14th, 15th century, they discovered frequency analysis. Yeah, they noticed that some letters show up more often in an alphabet, and that helped break a lot of algorithms. So, well, let's skip that. This here is important. This is called the one-time pad. It was discovered or invented in the 1880s and then reinvented around 1920. So the name pad just means a notebook, and the name one time means you use it just one time. That's a possibility to send a message 100%, it's called information theoretically secure. That means no computer, no matter how powerful, could break the cipher. Yeah. So the way it works, you need to have a random key, which is at least as long as your message. It's important that it's random, at least as long as a message, and that you use it only once. And it was actually proven by Shannon 20 or so or 30 years later. This is what's called information theoretical secret. No one can break it. No computer, no quantum computer can break that. And that's what people actually did. If they really wanted to have ultra high security, they used a one-time pad. And I read that the hotline between the President of the United States and the President of Russia is using one-time pad cryptography. Now, you know, the problem is, okay, how do you ship this stuff around? Yeah, like in the time between like the Second World War or so. Yeah, it's a huge logistic problem to produce this one-time pad, ship them around. So it's, in theory, it's great, it's being used, but it's flawed in practice. Here is, we're talking about symmetric cryptography, meaning the key, there is one secret key between sender and receiver. Now, what's used today is the advanced encryption standard, so that's a symmetric key algorithm, and it was established by NIST, the National Institute of Standards and Technology in the US. Now, the biggest problem, like in 2,000 years of cryptography, is when you have symmetric key distribution. Before you can exchange a secret message, you have to have a secret key. Now that's a typical what the Americans call a catch-22 situation. So catch-22 in culture means it's an absurd, it's a bizarre, it's a strange, it's a tricky situation. I want to send a secret message, but in order to do that, I need a secret key. So I don't know where to start with. So that's the fundamental problem of cryptography for 2,000 years. So, and that's what actually, if you really want to have ultra high security, yeah, you actually have people transporting the key to the bank at the other end of the planet. Yeah. Well, either you do it yourself or you trust someone and then you do that. Now, this here, because some of you know them, they came up with just a completely counterintuitive solution. It's just as baffling, I think, as quantum physics. And they realized you actually don't have to meet to agree on a secret key, and you can actually establish a secret via a public discussion. So even if someone is listening in, you can still establish a secret key. Totally baffling. So it's called public key cryptography. So just a short recap how this works. So you have two different keys. You have a public key and a private key. So Alice is using the public key of Bob to encrypt the message that she would like to send in secret to Bob. She's sending it, people can snoop on it, no problem. And Bob is using the private key to decipher. The private key only Bob knows. Now, when Diffie, Hellman, and Merkle figured that out, they were trying to put this into mathematics, and what they were looking for what's called a one-way function. This is a one-way function. If you scramble, if you do what do you call it, scrambled eggs? Yeah, you cook a scrambled eggs. This is a one-way function. Or if you mix colors, that's a one-way function. It's easy in one way, but it's difficult the other way around, the way back. So how do you transform this into mathematics? So there was a race to find an algorithm which makes use of a one-way function, and the race was won by a team whose initials are RSA, and that's the RSA algorithm that's the most widely used to do today in public key cryptography, in asymmetric key cryptography. So I'm not sure whether anyone looked at the RSA algorithm. For you who are in computer science, did anyone look at the RSA algorithm? Okay, good, quite a few. So it's not too, it's not too long. Yeah, everyone will understand it if you go through how it works. The amazing thing is, how to arrive at this algorithm. So, and the key part of the RSA algorithm is that you have two primes, P and Q, and you multiply them and you get a number n. So the multiplying is the easy part. The factoring is the hard part. Yeah. Factoring is hard computationally. You know, we can multiply 3 times 7. That's easy. That's multiplying. Factoring, okay, we happen to know that 21 equals 3 times 7. But if the numbers get really big, then factoring becomes very difficult also for computers. So the way this then works is Bob publishes his N number, his public key. He keeps private his private keys. Then Alice takes this public key, encrypts her message, and so on. Yeah. Now, and that's important. Today, all the transactions on the internet make use of both asymmetric and symmetric key cryptography. So suppose Bob is the merchant and Alice, I think you can actually sit, Ida. I mean, you don't have to stand with the balloons here all the time here. Sorry about that. Yeah. So Alice is the customer and Bob is the merchant. So if you buy something on Amazon now, so the way it works is that the merchant is sending you the his public key, and then so here we have the public key. Alice's computer is coming up with will be the shared symmetric key. Yeah, only she knows it. Yeah, but she's using public key cryptography to encrypt the key to be shared, the symmetric key to be shared between the merchant and Alice. She sends it to Bob. Bob can decipher it, and now they have a symmetric key. And all the other transactions now take place using the symmetric key, like the transfer of the credit card and so on. So when you hit the buy button on Amazon, there's always takes a little bit of time. This is when the public key, this mechanism is happening. So whenever you buy something, you both asymmetric and symmetric cryptography is being used. So on the history, so these are the Diffie-Hellman did most of the work in coming up with that, and then here these gentlemen were the first to come up with an algorithm which now bears their name. And there is an alternative history, or I mean, it's not an alternative, but it's also part of the history. The British Secret Service came up with the same thing, just a little bit earlier, but they couldn't. You know, when both parties developed things at the same time, being at the Secret Service, it's a little bit difficult to publish things. Yeah. So, but that's also it's really very interesting to read this in the book. Okay, now for the crypto in the future, and that's important. So traditional public key cryptography is based on problems which are computationally hard. As the numbers get bigger, it gets more and more difficult for the computer. It takes longer and longer to do computations. But computationally hard problems are not information theoretically secure. So if the computer is powerful enough, then the algorithm can be broken. So a quantum computer is going to crack the RSA code. Now, what about quantum computer and symmetric key encryption? Can a quantum computer break symmetric key encryption? No, because symmetric key encryption is not based on factoring prime numbers. We haven't had this yet, but what a quantum computer is really good at is in factoring numbers. So we'll just take this for granted now. So that's why a quantum computer can crack the RSA algorithm, but a symmetric key is just a random number of digits. The quantum computer cannot crack that. But because all purchases here, all communications on the internet make use of both symmetric and asymmetric key encryption, if the quantum computer can break RSA, then the whole commercial cryptography system is going to break down. So there is a solution to that, and that's called quantum key distribution. And the big difference is this is information theoretically secure. It's based on the law of physics. It's not based that the problem is computationally hard. So that's a fundamental difference. So this is information theoretically secure. No quantum computer can crack that. A quantum computer is probably harder to build than QKD systems, but replacing the current telecommunication infrastructure and upgrade it to make it quantum compatible will take a long time. Will probably take longer than actually developing a quantum computer. And therefore, it's urgent to do this now. It's urgent to do standardization now. When we had our discussions at the TSAC meeting, there were comments made, well, quantum computers are going to take a long time. Do we have to do that? Are we a research institute? It's true, it will take a long time, we'll get to this point, for a quantum computer to actually crack an RSA number. So, but still, if that's done, upgrading the infrastructure is just, it's just whenever you have a legacy infrastructure, it's horribly difficult to upgrade it. So that's why it's urgent to do this now. Okay, on the history that this was developed, there was a gentleman called Stephen Wiesner. He was a graduate student at Cornell University, and he came up with a fabulous concept called quantum money. Ingenious concept, but totally impractical. Vijay, I don't know whether Vijay is here. This is something maybe that might be of interest. It would maybe cost like $1 million to make each dollar node secure, so that's not really worthwhile. But he had some brilliant ideas. He tried to publish it. No one understood it. His senior advisor was not interested. He was able to publish this like 15 years later. But he talked about it to this gentleman called Charles Bennett. So he is at IBM. He's been working for decades at IBM. And the two, Sarah and Bennett, they came up with, in '84, with a protocol. It's called the BB84 protocol. Again, they tried to publish it. It was published in some obscure conference proceedings, and the world didn't catch on it. And then in 1991, a gentleman, he's a professor at Oxford, I think, Arthur Eckert, he came up also with a QKD algorithm, but based on entanglement. Practically speaking, the BB84 is easier to use. So I'm going to explain this to you and not the other one. So that's sort of the history, how it started. So, okay, I'm going to explain this to you, and I think everyone will, you will be able to understand it. Maybe not everything now, but if you think about it and you read up on it, you will understand it. So again, let's see what we're trying to do. We're trying to establish a secret key. We're talking about symmetric key cryptography. We're trying to establish a symmetric key. Yeah, and if someone is snooping in, listening in, it shouldn't matter. Yeah, information secure, theoretically secure. So we have a light source, a photon. The photon is hitting a glass filter that's absorbing most of the photons, and just like individual photons are being sent to Bob. Now Alice has polarization filters vertically and horizontally, and diagonally, plus 45 degrees, minus 45 degrees. Bob also has vertical and horizontal and diagonal filters. So what Alice will be doing, she will be sending, forget about the numbers, we'll come to that on the next slide. So she's going to send individual photons to Bob, and she's going to polarize them randomly. Bob is measuring the photons, and he's also selecting the filters randomly. And the protocol that I'm going to show you will establish a key that's proof. Even if people listen in, you will not be able to crack it. So this is how it works. So we have on the Alice side, we have a rectilinear scheme. And actually, Alice you will see that she will call Bob, and she will say which scheme, either the rectilinear or the diagonal, she has been using for sending the photons. Okay, so suppose, let's look at the top thing here. Suppose Alice is sending a photon which is vertically polarized, and suppose Bob on the other end is selecting the rectilinear scheme. So that means all the photons that will leave Alice are also being detected probably by Bob. Okay, fine. Let's look at the second scenario. Alice is sending again photon vertically polarized. Now suppose Bob, because he's choosing everything randomly, has chosen the diagonal scheme. What is going to happen then? Then there is a 50-50 chance that the photon will be either in this polarization or in this. Yeah. So, and the same for the other one. So look, if we look at the diagram, if you look at the last scheme here, Alice sending a photon which is diagonally polarized. Bob chooses this polarization state, and you know, this is what we learned basic quantum physics. The probability of measuring the photon in one or the other state is 50%. So Alice is sending. This is supposed to be the key. That's This is a random sequence of bit, and the idea is to establish a key that's really random. That's a key that's really secure, that cannot be cracked by someone listening in. So she is choosing randomly the polarization scheme, plus or minus. And when she chooses plus, because 1 means, from the previous slide, 1 means she has to use this vertical filter. Yeah, she's sending a vertically polarized photon, and so on. As for all these photons. So in this scheme, let's look at the very top row here. Alice is sending a vertically polarized photon. Bob's detector, let's suppose he has chosen this configuration, so he detects the proper photon, and Bob's bit is correct. If he chooses the wrong or different scheme, then there is a 50% chance that he's detecting the right or the wrong photon. So you can do this for all this combination. That's very simple. I mean, you will have to just, if you take time, it's easy to understand. So what Bob is then measuring. So the first 3 rows, I think we understand. So what Bob is detecting on his side. So he's choosing the detection scheme, again, randomly. And this is what Bob is measuring. So let's look at the first column. Photons come in vertically polarized. Bob happens to choose the right configuration. Yeah, that's the plus sign. So Bob's measurement is A1, and so his 1 coincides with Alice's 1. Now let's go to the second column. Alice is sending a 0. She's using this scheme to send a 0. But Bob is, by just chance, taking the other detection scheme. So there is a 50% chance that the photon is either this way polarized or this way polarized. So let's say just he happens to measure the right photon so that his photon coincides with that of Alice. So we can do this for the whole thing. And then Alice calls up Bob. They speak openly on the phone. That's so people can listen in. And Alice says, I was using for the first photon the rectilinear scheme. For the second one also. For the third one, I was using the diagonal scheme. I was using for the fourth one the rectilinear scheme, and so on. So Bob will know when his measurement coincides with the one of Alice, and they will only retain those photons. So you see some blank spaces, they will be omitted. So, and then the key is this. So suppose in real life you may maybe choose a key of 1,000 bits. Yeah. So you will have maybe you start with 2,000, and then you end up with a key which is maybe 1,500 bits or so long. Yeah. So that's how the key is established. Now, why is that secure now? Suppose we have Eve who is eavesdropping. Yeah. So there are 2 reasons. Suppose Eve is able to divert all the photons that come from Alice that go through Eve, and then they go to Bob. Eve is in the same situation as Bob. She will choose her detection scheme randomly. Now suppose that by coincidence she got all the configurations exactly the same as Bob, like all the 1,500 or so. Yeah. Okay, then she would know the key. But that's completely impossible. Yeah. So there will be photons where, if we take the red one. Here, the red column, so Alice sends, wants to send a 0, she uses the diagonal polarized scheme. So Alice and she uses actually then this polarizer. So this is, I think, this is a 0 state. And now suppose, Bob would have used the X one, but Eve uses the plus one. So that means the photon is either vertically polarized or horizontally polarized after the photon leaves the detector of Eve. So there's a 50-50 chance that Bob is measuring like either 0 or 1. So there will be some numbers where Bob will get the same result as Eve had, but there will also be other occasions where she will not. And so what needs to be done then is that Alice and Bob call each other and they take, let's say, 50 bits. They choose some randomly 50 bits, and this way they will find out whether there was someone snooping on the line. Because if it turns out that like out of these 50 bits that they think should be 100% identical, if it turns out that maybe 20 are not, that's a sign that we had someone snooping on the line. So that's the reason. So this is how this works. And so they have now a key, which is information theoretically secure. No quantum computer can crack that. So again, here is a summary. So Alice and Bob, they're sending each other photons. The idea is that the photons being sent are part of the key that may make up the key. Alice tells Bob for each photon that she sent, which polarization scheme she used. And so Bob will know which photons she measured correctly. Then Alice and Bob call each other. They discard the photons that Bob measured incorrectly, and then they do this integrity check to make sure that no one was snooping on the line. So maybe a little bit, you have to, if you read up on it and think about it, it's easy. Everyone will understand that. So that's just ingenious to come up with this protocol. So when they did the first experiment, they did it like 5 years later, and the computers were separated by like 30 centimeters. In 1959, the University of Geneva did an experiment. So that's a famous experiment between Geneva and Nyon. It was they were using optical fiber. So that was 23 kilometers. Then in 2007, the state of Geneva installed the world's first commercially available QKD system. So when they had a vote, and the Swiss government, they were sending the results using QKD from the ballot center, from the ballot counting center to where the stuff is getting stored. And I think that's probably still in use. So that was 2007, the state of Geneva. Here is a paper in it's a famous physics journal here that dates from November. Here they secure quantum key distribution of 421 kilometers on optical fiber. So that seems to be the world record on optical fiber. Now, if you go to China, I mentioned the satellite that China had launched. They were able to do quantum key distribution using with photons going through the air. And so here are numbers that they came up with. Yeah, they are able to have a kilohertz key rate over a distance of up to, that should be 1,200 kilometers, not 1,200 meters. Yeah, and that's amazing. So that's 20 orders of magnitude more than what you can do on optical fiber. So 20 orders of magnitude, that's huge. It's not a factor of 20. It's 10 to the 20. Yeah, that's quadrillion times 100,000 or something. That's a huge improvement. But still, it's pretty low. Yeah, it's kilohertz rate, and there's not maybe much that you can do with right now. But it's just amazing, that this is possible now. Okay, quantum computing. Shall we do that? All right, quantum computing. So names that come up is Richard Feynman. Here is a book called Surely You're Joking, Mr. Feynman. Anyone has read that perhaps by any chance? So he's a Nobel Prize laureate. Yeah, pretty interesting, entertaining book. Then David Deutsch, he wrote a book. So he's a prof at Oxford, I think. He wrote a book called Fabric of Reality. You really think you are on a different planet. He's the one who strongly believes in this many worlds interpretation. Then Peter Shor. So Peter Shor is the man who started the whole craziness about quantum computing, because in 1994 he came up with an algorithm called Shor's algorithm, and I'm going to explain to you a bit how that works, which actually was a practical algorithm where people saw that they actually could do something interesting with a quantum computer. So 1994, he came up with this algorithm, and this is an algorithm to factor numbers. Yeah. So yeah. And then there is another algorithm of Grover that's for searching databases. That also presents a speed up. But it's not quite as spectacular as Peter Shor's algorithm. So I'll give you maybe the key message at the beginning, and then I'll repeat it at the end. So the way quantum computing is often described is, that you have this superposition of state, and in a classical computer you do things sequentially, but in the quantum computer you can everything in parallel, and you get the right result because everything is done in parallel. That's not right, because at the end there always has to be a measurement process, and you only get results you never know what the probability is that you get results with, so that doesn't really help you. So the right way of thinking of quantum computing is that you have to choreograph your algorithm in such a way that the amplitudes that will lead to the right answer will reinforce themselves, and the amplitudes that would lead not to the right answer will cancel each other. That's the key thing about the way quantum computing works. And I mean, coming up with algorithm in general is very hard. Even in classical computer science, multiplying two numbers, coming up with algorithm is really hard. Quantum computing, to come up with algorithms is even harder. So I need to explain something beforehand, which is called the complexity. What's it called, Alex? Computer complexity. It's how difficult it is for algorithms to do stuff. Suppose I ask you to write down. Pardon me. That's part of the terminology. Yeah? So suppose I asked you to write down a number. Suppose I asked you to write down on a piece of paper the number 100, and suppose it takes 1 second for a digit. It takes 3 seconds. Suppose I ask you to write down the numbers from 1 to 100. It takes 100 seconds. Suppose I asked you to write down the number 1,000,000. It takes 7 seconds. If I ask you to write down all the numbers from 1 to 1,000,000, it takes much longer. Yeah. So on the left-hand side, this is a linear relationship, the number of digits and the amount of time things take. The thing on the right, that's an exponential relationship. So this is very important. Yeah. So computer scientists talk about that algorithms take polynomial time or take exponential time. So polynomial is the thing on the top here. So you have a fixed number k. K can be 1, 2, 3. In the previous example, yeah, it was linear, k was 1. So that's a fixed number. So the number of the problem, the number that's varying, that's the n. Yeah, so that's a polynomial if the n is where it is right now. Now below, the n is in the exponent. So you need to maybe know a little bit of math to appreciate that. So this is a much, much faster growing function than any polynomial. Exponentials are very hard to have an intuition for. I mean, you know the story about the person who invented chess, and then he was asked what kind of reward would he like to have, and he said, not just have a grain of rice on the first board of the first square of the chessboard, then double on the second, doubled on the third, doubled on the fourth. Okay, that doesn't sound like a whole lot. So the emperor agreed, but at the end, if you do the calculation, it's huge. It's like the entire world production, or I don't know what. Or the other example is, if you're asked, if you have a sea with flowers, and every day the flower is reproducing, is doubling. When is the sea or when is the lake half full? It's not, suppose it takes 50 days to make the sea being covered by all the flowers. It's not after like 25 days. Yeah, the sea is half full after 49 days. So it's very difficult for us to have a feeling for how fast exponentials grow. So a lot of algorithms are exponential in time. So that means they're really very, very hard. The bigger the numbers get, the more difficult it gets. Really, classical computers can't do that. For polynomial, that's much, much faster. So what Grover's algorithm was able to do, so we don't go into details, was able to go from is a search algorithm for databases from n to the 4 to n to the 2. So that's an improvement in polynomial time. Yeah, you go from n to the 4 to the n to the 2th power. Okay, that's not bad, but we'll see that the improvement by Peter Shor for his algorithm is much, much harder. So I'd mentioned, you know, factoring, multiplying is easy, but factoring is hard. This is the largest factored number into 2 primes. So remember, we had the in the RSA algorithms, the key piece is that the number, your public key, is being composed of 2 prime numbers. So here are 2 prime numbers, the one at the bottom. Yeah, if you multiply them together, okay, I guess you can do that, and the computer can do that, yeah, easily. You get the number on the top, but the reverse is just, it's too hard. Yeah, computers today cannot do that. This is what you find as the running time of factoring algorithm as the numbers get bigger. So what I did just, you know, suppose, you know, we saw on the previous slide, the highest, largest number that was factored into 2 primes, it's called RS768 because it's in binary, it has 768 digits. If you translate it into decimal, you get 232 digits. So let's go to 1024 bits, which is higher than the highest numbers that has been cracked so far, at least as far as we know. So you just plug in the number here, and then you get 10 to the 30 operations. So I looked up, you know, what's the fastest supercomputer today? It seems to be, it used to be in China for a while, but I saw on the internet, like in June, there was an announcement that the US has a computer with 200 quadrillion operations per second. So when we don't know what a quadrillion is, so we look it up, 10 to the 15th. So that's 10 to the 17th operations per second. So now I plug it in and convert it into time. We get about 300,000 years. That's what it would take if you use the best algorithm, which is called field sieve algorithm, the best algorithm to factor numbers. So maybe it's 100,000. I mean, it gives you an order of magnitude. You know, it's not 10 seconds. It's not an hour. It's a long time. And now take a guess how fast Shor's algorithm is. B to the 3. So that's unbelievably fast. You know, that's done in, I don't know, a second or so. This is why there is all the noise about quantum computing. It will make our security, our RSA algorithm insecure. It will be able to crack it. This is how good this algorithm is. Okay, I'm going to explain you now how the Shor's algorithm works. It comprises a classical part that's done with a classical computer, and then there is a part that's being done by the quantum computer. So there is a toolkit with like 4 different tools from classical mathematics that you need, and then there is a quantum part. So the classical part is easy. The quantum part is a little bit rough going. Let's do the classical first one. So one thing we need to understand what's called modular arithmetic. That's the arithmetic of the remainder. So the Americans, when they quote the time, 9 a.m., and then they add 4 hours, they don't say 1300 hours, 13 hours. They say 1 o'clock, 1 p.m. So the way you arrive at that, so the way the American clocks work is based on the modular 12 principle. So 9 plus 4 is 13. You divide by 12, that's the modular, and then you keep the remainder. So that's called modular arithmetic. So you may wonder, why is it useful? People were playing like numbering people were playing around with modular arithmetic, like Gauss from Gaussian distribution, did quite a bit of research on that. So mathematicians like to play around with it, and then it turns out to be useful 300 years later for something. So here's an example, and there is a reason why I quote this. Let's suppose we have a function which is called 2 to the x modulo 21. Yeah, so that's an easy one, 2 to the x. So let's start with x equals 2. Yeah, we plug in 2 for x, so 2 to the 2 is 4. Modulo 21, no problem, so that's 4. Let's look at x equals 5. 2 to the 5, that turns out to be 32. modulo 1, you divide 32 by 21, you keep the remainder, that's 11. So remember this maybe perhaps for the next slide. So there's a sequence 1, 2, 4, 8, 16, 11. And then it starts again 1, 2, 4, 8, 16, 11. You will, not obvious now, but that's actually what it is, yeah. So that's easy. So the second thing we have to understand that functions can be periodic. It's easy for continuous functions. You know, we have sine waves, cosine wave waves. So they are periodic, but you can also have periodicity for discontinuous functions. Here is what I showed you: 1, 2, 4, 8, 16, 11, 1, 2, 4, 8, 16, 11. It's going to repeat, so that's periodic. So that's the second piece we need to know. The third piece that we need to know is when you have a wave, you can describe it in time, but you can also describe it in frequency space. Yeah, you may here and on the left-hand side, I have a description in time, but you can also describe it as a value in frequency space. And this thing, there is a machinery. Every engineer knows how this works. It's called Fourier transform. You can also have this transformation with discontinuous functions. So below, 1, 0, 0, 0, 1, 0, 0, 0. So the period is 4, but the period is also 8 and 12 and 16. That's why you get different peaks in the frequency space. So that's the third piece that we need to know. And then the fourth piece, that's the Euclid's algorithm. Everyone will understand that. So that's how to find the greatest common divisor of a number. Let's say 18 and 14. So the way you do it, 18 is 2 times 9, 9 is 3 times 3. 24 is 2 times 12, 12 is 2 times 6, 6 is 2 times 3. So the greatest common divisor is 2 times 3 is 6. And there is an algorithm. Euclid apparently came up with this already. So that's the fourth piece that we need. So now the insight, the key insight, but that's not Scholl's insight, but that's one of the two key insights, is that, wow, miraculously, this factoring of a number is closely tied, maps into the ability of finding the period of a function that's a to the x modulo some number. Yeah. Wow, that's just okay. Wow, the numbering people came up with that. And maybe if we spend some time, and probably we could maybe understand that, but let's just believe that's the way it turns out to be. So that's, wow, it's amazing. So if we want to factor a number, yeah, a prime, then what we would do, we would take the function here and try to find the period. And there's another question whether this is really fast enough. Yeah, but it turns out for the quantum in Scholl's algorithm, that's really fast. So you do a mapping of this problem into this alternative way of formulating it. So that's amazing. This is Scholl's algorithm. So you have a number n that you would like to factor. So you calculate this function a to the x modulo n, and you try to figure out what is the period. Yeah, so that's the tough part. And to determine the period, that's what you use a quantum computer for. And then once you find the period, there is a formula that gives you the two primes s and t. So that's Scholl's algorithm. We do it for 21 equals 3 times 7. Yeah. So let's look at the first line. So we choose n equals 21, and let's just choose, we could choose another number. Let's choose a equals 2. Yeah, so we have this function to the x modulo 21. We have looked at this before. We know that the period is 6 here. You plug in 6 in the equation s equals greatest common divisor. You get 3, and you plug it in for t, you get 7, and you have the primes. That's how it works. Yeah. So that's easy, but it gets very difficult if the numbers get big. So, well, maybe I'll just, I think maybe I'll skip that here perhaps, or should we, so this, the interesting question is, if what is the period for functions that look like that? And just to show you an example here, like the number of rays where you see dots on, where you see dots, that's the periodicity. If you count the number of rays or dots, that's the periodicity. So for example, for this function here, we have selected A equals 13, and n, okay, prime, that's n equals 19, you see that the period is almost, pretty much all the ways are covered except 0. The period is almost as high as the number. If we want to plug in, something else, we had A equals 2. That's the example that we used. And then we had modulo 21. Oh, okay, yeah, it gets a bit 21. Yeah, you count the number of rays where is the dot sign, you have this periodicity 6. So in general, what do I do now? Do I stop this here? Do I just kill it here or? Yeah, okay. So there is no way to really predict the period, and the period could be basically as high as the prime that you're trying to factor. All right, now the ingenious insight. Okay, this is going, the right is going to be a little bit tough now. I'm probably going to lose you for 10 minutes. Okay, bear with me, but maybe some of you will maybe get a feel. So, but I think it might still be useful to see, how things actually work. Maybe the point again is the quantum computer is not just good at anything. You have to find an algorithm where it shows that's actually able to do something useful. And it just happens to be that Shor's algorithm is an algorithm that allows you to factor numbers, but it's not that you could use a quantum computer just for anything. You have to very carefully find a right algorithm. So that's another maybe key lessons before I maybe perhaps lose you. So Shor's ingenious insight was to use another Fourier transform, but something called then the quantum Fourier transform, acting on a superposition of states. So here is a flow chart on how things would work. I mean, this works on paper here, and no quantum computer has been built. I think they may have been able to do 21 equals 3 times 7, but they haven't gotten beyond that. They haven't been able to do something useful yet, but proof of concept, I think, is available. So here is a flow chart. And I'm going quickly through all these steps. So you start out, and we do this example for the number n equals 21. So you have a register on your left-hand side, and so you divide this into two parts. One is part 1, one is part 2. One holds x values, and the other one the f of x, this function, this modular function. Then it turns out that for this number we need 9 qubits. So 9 qubits, that is 512 basis vectors. Yeah, for the qubit, for 1 qubit it was 2. If you have 9 basic vectors, then we have 512. So the nomenclature that could be used is either I will write 9 times a 0, and then 8 times 0 and 1, and so on. But that's a lot of writing here, so I may also use a decimal notation. Now in step 2, there is an operation. It's called equally weighted superposition of all integers from 0 to 511. You will understand that. So that's somehow possible. We didn't go into that. You can apply gates, like the same way you apply gates in classical computer science. You can also do this with quantum gates. So you apply this operation, and you see they're equally weighted because the probability here, 1 squared of 512, that gives you an equal probability of finding the system in any one of the states if you do a measurement. Okay, step number 3, you apply a transformation, this modular transformation for each number, which is stored in your register 1, and then you store the result in this register 2 here. The way, okay, I'm skipping some things, the way this can be written is the way I have it, and you just calculate, which we already did, to the 0 modulo 21, to the 1 modulo 21, and so on. You get the line below, and you can see that you can group it this way. So we have, at the right, if you look at the right-hand side, you have 1, 2, 4, 8, 16, 11, these numbers in these states. That's the periodicity of the function. And then you have a bunch, around 85-ish terms that have that map to that. You take a measurement of register 2, and then you have an equal probability of finding one of these numbers, 1, 2, 4, 8, 16, 11. Well, let's suppose our measurement yields the number 1. Then we have in register 2, then we have in register 1 this combination 0, 6, 12, 18, and so on until 510. And if you compute the quantum Fourier transform on that, this is what you'll find. You'll find the probability of measuring the outcome, and you find a high probability for the number 85, and then 170 or something, 250 or so. And for the other numbers, the probability is basically 0. And so when you do a measurement, let's suppose we call this measurement 1. So there is a high probability that your system will be in the state in a multiple of of these numbers. And suppose we actually end up with 85 in our measurement, then we divide 512 by 85, and then we end up with 6, and that's the period. And it's more complicated if we get another measurement. So I have lost you here, but that's sort of just to give you a feel for what's implied here. Again, the trick here is you have to carefully choreograph your algorithm, and you have to just figure out that this is the way that somehow seems to give you a good result. That's what you have to do. I think I'll just skip that here. I'll skip all of this here. And so we're coming to the end. What's actually doable? Did I click so fast here? Okay, we skip. So again, what's wrong? What you often read in the papers, and this is actually a statement from a book: a quantum computer will try all the possible factors simultaneously and then collapse to reveal the answer. That's not what's going to happen. Yeah? If you do a measurement, you get with random probability, some outcome. You have to choreograph your algorithm to make sure that if you do a measurement, there is a very high probability that you get the right result. So that's amazing, but it's wrong. But the correct answer, but that's maybe less exciting, is that a quantum computer is good at finding the period of a function. So if you ask what has quantum computing to do with factoring, nothing. Well, but quantum computer has everything to do with finding the period of a function. So that's the secret. So Shor's algorithm is carefully choreographed. Okay, so it's complicated, but it will allow you to find the period. And the interesting thing is this is a probabilistic algorithm. You don't know for sure that you have the right result. Yeah. For example, it turns out if R, you might remember this R, if that's not an even number, okay, bad luck, have to do it again. Yeah. So there is a certain probability, but again, if you do calculations, you can show that luck will occur with a pretty high probability. So that is interesting. Is a quantum computer digital or analog? It's perhaps maybe sort of both. Digital, the information is acquired only when you measure qubits, but it's analog before you do a measurement. And again, again, the key is it affects the amplitudes, probability amplitudes. You have to choreograph it so that the ones that lead to the right answer are amplified and the other ones are deleted. Classical computer, time is precious, but bits are cheap. For quantum computer, it's the other way around. So what's the smallest useful quantum computer? If you want to run Shor's algorithm for a 2024-bit number, so that's a sizable number. Remember, the highest RSA number that has been factored that you do primes was 768, I think. Yeah, so that's a 2024-bit number. It turns out that you don't need only 1024 bits. You actually need, there is overhead. We didn't talk about quantum error correction. So there's quite a bit of overhead. You need about 5,000 qubits. So that's far beyond anything which can be done today. So this is certainly not going to be the first application. Instead, there are applications like modeling some quantum chemistry or something in machine learning where people think that this could be applied. There is a term called quantum supremacy, which is a little bit controversial, but it seems to catch on. That means a problem that can be solved by a quantum computer, but not by a classical computer. An interesting question is, what's the largest quantum computer that can be simulated by a classical computer? So it thought that for about something like 50 qubits and higher, you would be able to do some things that a classical computer could not do. Qubits are very fragile. It's very difficult to produce them in the lab. And you need a lot of quantum error correction. Again, that's a separate science. Peter Shaw also did a lot of work on that. So the term that's being used like right now is called noisy intermediate scale quantum NISQ devices. So the idea is, what can you do with 50 to 100 qubits, but without any error correction? This is what's predicted for the next 5 to 10 years. That's where the research, that's where the industry will be going. What is it that you can do with 50 to 100 qubits without any error correction? So here, status of industry. IBM is doing a lot on it, and in Las Vegas last week they announced something called IBM Q system. So this is what I copy-pasted from a press release: the world's first integrated universal approximate quantum computing system designed for scientific and commercial use. Not quite sure what that means, but okay, fine. They also have a 50 qubit undergoing testing, and all of these technologies are based on superconducting electronic circuits, and that's why these things look so big, because it's a refrigerator. Google is doing work on it. Intel is working work on it. There is a company called Rigetti that's doing work on it. I didn't find the latest data on Microsoft. They're doing a lot of research. And China. I mean, China is a leader in quantum computing and this quantum communication. They are sort of the superstars here, together with some of the US companies. So that's the current status. I think maybe I'll just stop now. I don't have that much to say about maybe the quantum internet. The idea for quantum internet is that you don't send bits, you send qubits. Yeah, and also that you try to create an entanglement between any 2 points, and we'll figure out eventually, Stefano, why this is useful. We have seen the University of Delft is has a very good reputation. They want to build up a network with 4 nodes by 2020. Then the Chinese are, just great publicity, great difficult experiments that they have been running with their satellite. Just to give you some numbers, on what has already been done and how much still needs to be done. If you want to send fiber, entangled photons on fiber, you would measure about 1 entangled photon pair coming out at the other end every 30,000 years. Okay, forget about that one. But with the satellites, they were sending 6 million entangled photons per second, and 1 entangled photon pair actually per second reached the ground station. So, okay, I think I'll just skip that. Here is a paper, that's the last one, paper, it was published in Science a couple of months ago, which sort of lays out the path to the network. And the next thing is to go to what's called trusted repeater networks. With optical fiber, you can send photons up to qubits up to about maybe 200, 300 kilometers. So if you're going to go to longer distances, you have to have a relay that you do trust. If you try to establish a secret key, you cannot go to 1,000 kilometers. You have to have a relay in between that you trust, and that would also know then the secret key that you have. So this is the next step. That's, for example, what the Chinese are doing with 2,000 kilometer network from Beijing to Shanghai. Anyway, so the way to what might be called the quantum internet, still a lot of research needs to be done. A lot of engineering is incredibly difficult, and but I think it's just super exciting. Thank you.
Any question? Oh, many questions.
I have one. Yeah. Okay. You mentioned that TSB wants to focus on QKD, right?
You're asking me or
standardization on, if I'm not mistaken, on quantum key distribution. Is that correct?
That's one topic, yeah.
Yeah. So, doesn't standardization go against the randomness of producing the key, and wouldn't that weaken it?
The way to think about it is the QKD is giving you a symmetric key. Yeah, there is a mechanism. I mean, we don't standardize the American encrypted standard algorithms. We don't standardize that. But QKD gives you a symmetric key. Okay, but then you have a symmetric key. You have to, you have to bring it up the layers, your application layers. The applications will have to do. They will want to make use of the symmetric key. Yeah. So lots of interfaces maybe to be looked at, and management control, all of that, yeah, for a QKD network will have to take into account, not the algorithm, yeah, itself. Yeah.
Okay, thank you, Reinhard. You mentioned the 50 qubit computing, quantum computing is under processing, under testing, and the 72 qubit computer is planning. It means once 50 qubit computing is available, it is more supercomputing than existing traditional computer system. Then what the current cyber-related issues? Because it is really threatening near coming years. Is there any expectation?
Again, so I think everyone believes that eventually a quantum computer will be able to crack this RSA algorithm. Cracking means they're able to factor big numbers into primes, but that's a long way. Yeah, you need, if you want to do like a real sizable big number that no classical computer can crack, you would need like 5,000 qubits. And to have 5,000, a system with 5,000 qubits far beyond current technology. What's possible today is to have computers with, say, 50 qubits, but that would not be used to do anything, nothing factoring. You could factor maybe 21 equals 3 times 7, but we already know that. We don't have to do that. Yeah. But you would be able to solve other problems. I would have to look at, and I didn't look into that. So one thing which is believed might be useful is to do some quantum chemistry. You want to figure out how the small molecule is working, how something along these lines, or perhaps also in machine learning. So that's what the current state of the computing is. This quantum error correction, which we did not talk about, people at the beginning thought, because these qubits are like soap bubbles, they live for a few milliseconds, and then sort of the environment kicks in, and then you lose, they lose their state. That that's just going to be hopeless, yeah. But then also Peter Shor and other people came up with good quantum error correction methods, but they take quite a bit of overhead. That's why to factor a 1,000-bit number, you don't need just 1,000 qubits, which you may think this is what you need. If you take all the overhead into account, you actually need about 5,000 qubits. So that's just a long, long way to go. I think Martin was first, yeah, and then. Okay.
So Reinhard, first of all, many thanks for this exciting presentation. I think I learned a little bit, and I may not have learned everything. One question is, and I'm still struggling to understand where we are with this quantum computing. With the quantum teleportation, that's something easier because it's a communication thing. But with the computing, I'm not sure. And my reasoning is, if we look back in the past 50 years with the digital computers, binary computers, of course, at the beginning we saw lots of legacy proprietary equipment as big as this room. There was nothing standardized at all in this. They used some tubes, stuff like this, some wires, everything else was completely legacy engineered. Then the transistor came around, and with that, the uptake took place with the miniaturization in logic circuits, digital signals, integrated circuits. And from that point on, the computer became a commodity product. What we have here, the general purpose computing thing. So I'm not sure where we are with this quantum computer. These exciting fridges that you showed from IBM and others. I don't see anything commonality from one provider to the other manufacturer. This is all completely different stuff. So where are we in terms of standardization? What do we need to standardize? And the second question is, what are the applications for the quantum computing? You mentioned, yes, factoring and database searching. I would call factoring is not a problem for anybody than the NSA and folks like that. So this is not for us. We don't factor numbers for our. But that would mean everyone would see what kind of browsing you are doing. But that's not something we standardize.
Yeah.
So I don't see the application for that. So you can build a machine and prove that the internet is insecure. So what?
Martin, I don't see you buying an IBM refrigerator either.
No,
yeah?
no, definitely not, because it's too expensive.
I mean, right.
And what could I do with that?
I mean, IBM is making what you may have is it's difficult to predict, yeah, where things will be going.
Well, but it fits into cloud computing. Yeah? You don't need a computer on your desk. You just buy the service.
You buy the
IBM can put 1 million refrigerators in their basement somewhere, and Amazon is almost doing that. So I see a lot of applications there.
But Martin, this is not just a problem for the NSA, because on one slide, I pointed out like every transaction that's taking place now on the internet makes use both of symmetric key and asymmetric key cryptography. Quantum computer does not break the symmetric one, but it does break the asymmetric one. So the entire system that's being used to encrypt credit cards, etc., would be available or would be broken by anyone who has access to a quantum computer. So it's not just a problem for the NSA, and the fact that eventually people believe, and we'll see how history plays out, but a lot of people believe eventually that will be possible. What may take even longer than developing a quantum computer, that's just getting all the telecoms infrastructure beefed up to take to make use of quantum key distribution, for example. It's pretty funny. The quantum computer is able to crack your RSA algorithm, but you can also use quantum physics in the sense of QKD to make sure that the quantum computer does not break asymmetric key cryptography. So that's pretty interesting that this is happening. Yeah. So you will have to beef up, to upgrade your telecom network. You will have to define, interfere, and 1,000 things that you will have to do, and that's urgent. So that's where standardization kicks in. I don't see that we play any role in quantum computing, but I think it's important to understand what the impact of quantum computing might mean for the network, and there will be an effect of the network. And because there is so much legacy stuff out there, you have to do this now. You cannot use the argument, okay, we'll take another 20 years for $200 quantum, and then we'll start figuring out, it's going to be too late. That's the argument that's being made.
Thanks, Reinhard. That's very interesting. Some authors that think the other way around, that it will come first the quantum internet with satellites, so for distribution keys, than a quantum computer actually, because quantum computers, there are plenty of concepts proving that it should work. But if you look from the point of view of an engineering, it may be almost impossible in some cases, because for error, as you said, error correction and noise suppression, it may be that it's not just 5,000 qubits, but you need much more. You need some redundancy. So some people claim that it will never come. But then a possibility could be these semi-quantum computers like the D-Wave, which was presented here like a couple of years ago, which would serve to solve some problems and using cloud computing, distribute services. Regarding the quantum internet, the solution with optical fibers doesn't seem to be good because of the interaction of the photons with the matter. But with satellites transmitting vacuum, it may be the case with the Chinese. So it may become first. So it may be that we have a way of distributing cryptographic keys using quantum technology without having actually quantum computers to make calculations.
Okay.
And then even if they are not used for factoring, the other use for simulating systems, chemical, physical systems, may also be very difficult. Because if in theory it works, looking at the specific problems you had with interactions with you said, error correction, it may become, some people made the calculation that if you want to really have something with 100 qubits or something like that, you may need to have kind of combination like 100 to the 300, which is more than the particles in the universe of specific devices.
Okay, yeah. I mean, no one has a crystal ball. Maybe yes, maybe no. We'll have to see. Yeah, I think it was Florence. You had some no, Christina. Yeah, Christina, you had. Yeah. Okay.
Sorry, thank you, and thank you very much for interesting presentation. For me, it was really good actually to learn about. I was wondering, because did this separate research more related to smart cities, whether you foresee a role for ITU in the quantum computing to address challenges related to smart cities, and in particular to the application on machine learning and artificial intelligence. For example, I read an interesting report on what Microsoft is doing in this area. Is there anything that you foresee for that?
I don't know. I don't know. I don't know enough. I don't know what I didn't look at what detail what quantum computing could do for machine learning. It's believed to be that could be an early application of what's currently possible, given the current state of research. So, but I don't have detail. I couldn't give you details. I think for a city, for a smart city, I think there's still a long way to go until this becomes relevant. Yeah, but yeah, I don't know. Ahmed.
Yeah, actually, my question is about the entanglement distribution network when we talk about quantum internet, but it's a bit more of a theoretical question, because from what I understand is that we don't know the states of a qubit before the measurement at all. So is it the case, or actually the measurement itself, the measurement action, change the status and the result
Correct.
of it,
Yep.
right?
Yep.
So I think this is what makes the entanglement as a concept, or the spooky action, doesn't fully work and have some sort of error, because the measurement action itself affects the result of the qubit, right? So we cannot fully depend on the results we know, because we know that our measurement is what affected it. It wasn't the results already there. That's what I understand. Is this right? Or?
I mean, the quantum teleportation works on paper 100%. When it's clear you can teleport the state of a photon, the polarization state of a photon, from A to B, and B can be the end of the universe. The mathematics gives it. It's there was no doubt about it. Yeah. Challenges to put this into practice, show it with an experiment, but there is no. I mean, it's your photon on the receiver side will look exactly the same as the photon on the sender side. Yeah, even though you didn't ship the actual photon, you just have this magic entanglement stuff that makes you have the polarization state show up at the other end, by just transmitting the result of the measurement. Yeah, just that's what no one understands why that is, but it just works out, and it that's the way it is. Yeah. Yeah. Okay, Tatjana, and then yeah, Tatjana. Yeah.
Thank you, Reinhard. You mentioned briefly in your slides.
You have to scream, Tatjana.
Mm-hmm. Thank you, Reinhard. You mentioned few in your slides, but can you summarize the seen so far limitations of the system?
Pardon me, the limitations?
Mm-hmm. Already previewed.
For the QKD system?
Yeah, and for quantum computing. We know what it is good for, to measure the function, the period of a function, factorizing, but what is it bad for?
So you mean the limitations on the QKD system, or the limitations on the quantum computers? Both. Well, the limitations on the QKD system is the length that you can transport photons. Yeah, on optical fiber, there is a certain distance that you can cover, and then the photons, the environment kicks in, photons get absorbed, photons get lost, so you can transport the photons only a certain distance, a couple of 100 kilometers. You cannot amplify that. In classical physics, you can amplify stuff. You have repeaters, but because of this no cloning theorem, you cannot copy a quantum state. Yeah, so you have to find a way around it. So how far you can transport your qubits, that's a limiting factor. Going through the air, that's what China did. Yeah, that's working. You have some atmospheric, turbulence, stuff, environment that's playing a role. So that's a limiting factor. But otherwise, once you are above the 10 kilometers above the Earth, the rest is empty space pretty much. So that's good. So, and on quantum computing, it's just the difficulty of keeping these qubits alive for a long time. A long time, it's not just like milliseconds or something. Yeah, I didn't look up the numbers, but it's like soap bubbles. Yeah, they live for a few milliseconds, and then you have to be able to do all your stuff within your time. Especially when when you have to things cool down, that's a challenge. So these are experimental challenges. Yeah.
You mentioned mainly photon entanglement in quantum
Mm-hmm.
computing. What about other elementary particles like bosons, electrons, which are correlated offensively? So they are charged and they have mass.
Yeah. So things are also being done with electrons, with the spins of electrons. Yeah. Then you have these superconducted circuits that's being used in quantum computing a lot. Yeah. And when these are, I mean, you could have, also have atoms in two states, like the example that I mentioned with the ground state and the excited states. This has been done. So experiments have been done with various parts, but the easiest is the polarization of photons. You use this as a two-state system. That's that seems pretty relatively easy for communication, for sending purposes. Yeah, and somehow for the quantum computing, a lot of these computers are based on the on superconductivity. We had Jung-hee, she had invited the D-wave computer. There is a bit, I didn't look into detail that there is a little bit of controversy about D-wave, whether it's really a quantum computer or not, because they're talking about I think over 1,000 qubits that they're able to handle. I didn't look into that. I just know, there is some bit of controversy, but okay. Yeah.
What they have is the annealing quantum computer, which is a semi.
It's a bit different,
it looks for some kind of distribution where you have maximums and minimums. It's only for kind of discrete problems, cannot solve some other problems.
Okay. Yeah, sure, yeah.
Thank you, Reinhard, for this presentation. I think I have 2 points to add after our discussion. The first one, when we're talking about the future or the difficulty of quantum computing, I think for me, the difference from traditional computing is that quantum computing is so new that it is not a generic computing function. We have to find a kind of problem and a right kind of algorithm which is suitable for quantum computing, which the whole understanding is not there yet. It's not like the traditional computing series. We have the Bohr logics, and we know how to do the mathematics, and we know the traditional von Neumann structure of computer, have a computing unit, have the storage to temporarily store the results, so that. But for quantum computing, all the elements, the algorithms, the problems are not understandable at this moment. The second point I would like to add to this discussion is exactly because of it's so difficult to put so many qubits together to have a kind of computer we understandable. Actually, the real format of a quantum computer might be a distributed one. The qubits might be distributed over the network. Therefore, we will need the QKD as a link even inside the structure of a quantum computer. This is another kind of thought.
Okay, yeah, good. Okay, that's it. All right. Thanks for suffering through 2 hours here. I hope you picked up a few things.
Yeah, it's more than suffer. It's almost a torch. My brain is almost hitting. Yeah. Anyway, yeah. Let's upload all this, Reinhard. It's a even great challenge. It's a very complicated subject. Let's say this is the first really initiative as a kickoff of this our TSB talk. Second talk will follow. So we planned once or twice in a month. We continue with this TSB talk. Mainly, we start with this very ambitious futuristic subject, but we are going down as whether we continue to challenge of this, all the details, what has going down in the ITUT study groups and the focus groups. So it would be a good chance within TSB, sharing of this information, all the details, knowledge, also some of outside of TSB colleagues, yes, good opportunity to understand. Next subject should be, we are much level down, but still complicate, like a digital financial service. So Biller will prepare of this now. So we are, one of our strategies, we start from management first, showing as a reference model. So, and then following of this, all our study group counselors will follow that. So this is, we planned, as soon as we set up of this, all this plan, we can announce so our long-term plans to pencil over your schedules. So next should be available with the digital financial service by Biller. Okay, thank you very much.